This mixing tank problem is a little bit different because the inflow and outflow are different. So in this case, we have 3 liters per minute coming in, but only 1 liter per minute going out. So we'll have to deal with that inside of the ODE. So in order to do that, right, it's the same thing as before. So it's change in Q, or change in, grams of salt equals salt going in minus salt going out. So let's go ahead and compute those. So, right, change in salt, so that's dq over dt, right, and that's going to be in grams per minute. Minute. Okay, that has to equal salt going in. So that's going to be the 3 liters per minute times the concentration going in, which is 0.25 grams per liter. And we have minus the salt going out. So normally that's Q over the volume. And so now here it's the difference. So normally in the past, the amount going in and the amount going out have been exactly the same. So the volume throughout T was just some constant. But in this case, it's going to be 250 liters plus 2T. The reason it's 2T is we have 3 liters going in, we have 1 liter going out, so every single minute you're accruing 2 more liters of liquid in the tank. Right, so in the first minute, after the first minute, 3 liters come in, 1 comes out, so then that is a surplus of 2, so you get to 252. If you plug T equals 1 to here, you get 250 plus 2 is 252. So this is now the volume at time T that we have to use. So now the concentration in the tank is now Q of T over the volume of T, the amount in the tank, grams per liter, right? So Q grams of salt at time T, and there are V of T liters at time T. So in here, that's going to be Q, I'll put the of T for emphasis, over V of T, and that's in grams per liter. And then still we're going to be multiplying by the flow rate out for the amount that's leaving. So it's going to be 1 liter per minute. All right. So all the units are agreeing. So again, the liters cancel and we just get grams per minute everywhere. So we can rewrite this as Q prime is equal to, so 3 times 0.25, that's 0.75. We've got a minus. And so we end up with Q over 250 plus 2T. And that was all multiplied by 1, so it's just the Q over 250 plus 2T. Right? So next up, we have to solve this, and let's go ahead and use integrating factor. All right, so we have Q prime plus Q, and I'll separate this out to make it more obvious what the function is. So that's 250 plus 2T times Q equals 0.75. All right, so integrating factor, mu of T equals E definite integral 1 over 250 plus 2T. All right, dt. So it looks like that's going to be the e to the natural log absolute value. Okay, so I think it's 250 plus 2T, but I think we need a 1/2 in front. So let me see if I can squeeze that in. Right, when you take the derivative, you're going to get the 2T on top, and it's going to turn into 2. So to cancel the 2 on top, you have to preemptively multiply by 1/2. Right, and so that's almost simplified. We do have to put the 1/2 inside the natural log. So it's the same thing as e to the natural log absolute value. If you put the 1/2 as an exponent, it's 250 plus 2 to the 1/2. So 250 plus 2t to the 1/2, which the e and the natural log can cancel, so we'll end up with 250 plus 2t, and then to the 1/2 power is a square root. So apparently this is our integrating factor. So then going back, we'll end up with square root, sorry about that, square root of 250 plus 2t close the square root, q prime, plus, all right, if we multiply by the square root, I think we just end up with 1 over the square root, so we'll end up with 1 over square root 250 plus 2t times q equals, let's see, so 0.75, and then we've got our 250 plus 2t. All right, so from here you can do reverse product rule. We have to integrate this one again, which isn't so bad. I am running out of room here, so I think I'm going to move. I'm just going to write down the answer. So, do remaining steps. You'll end up with q at time q of t, the function, is going to equal, it's a constant over the square root of t plus 125, and you have plus t plus 125 over 2. And then if you solve for the constant of integration given our initial condition that q at time 0 equals 0, you would end up with, right, so you have to plug in t equals 0. It looks like you get some square roots. I think you get a 125 to the third over 2. So q of t with the initial condition is going to be, this ends up being a negative number. So it's, let's see, 1/2, so I get my 2 here, my square root of t plus 125. Let me make that a little cleaner. On the top is negative 125, and that's to the 3/2 power, so I'll just put 1.5, and then you still have your plus t plus 125 over 2. All right, so I ran out of room, so I couldn't do all the remaining steps, but this really we're emphasizing here how to handle when the inflow and outflow are different numbers. And when they're different numbers, instead of having a constant over your q for the concentration in the tank, you have to have a function of t, and that the function of t is what the volume in the tank will be at time t, and you're always accruing a little bit more each time. So you have a net 2 liters flowing in every single minute. So then the volume at time t is the initial 250 liters plus 2 times t minutes for the more liters at every value of t.